Okay, welcome to our first lesson in Unit 2, Equilibrium. This is an extremely important concept in the course, one that's going to not just show up in Unit 2, but the concepts here are going to carry through the rest of the course as well in future units. Okay, so we've kind of mentioned in Unit 1 very briefly that reactions can proceed in both the forward and reverse direction. And we saw that with our potential energy curves. So we're going to look in more detail at what's going on in those forward and reverse reactions. Okay, so in this little analogy here, this image, we see that in the forward reaction, if we just wait 1 second, in the forward reaction, we see right there some of these reactants are being converted over into the product pile. But at the exact same time, this little guy right there is taking some of the products and taking it back to the reactant pile. And so really we're just trading off. As some of these materials on the left get converted to other materials on the right, the exact same time materials on the right are converted back to materials on the left. Okay, so if we didn't see what was going on in the middle, what would it look like was happening? We would just see two piles staying exactly the same size, because as we lose some, we gain some back at the exact same time. And this is going to lead us talking into this dynamic equilibrium. Dynamic kind of leading us to say that things are happening. There are things moving around in there. We just might not see them. Okay, so this idea that reactions are reversible. Okay, all reactions are theoretically reversible. It's just that some are way more likely to happen on their own, at least spontaneously. So if we compare these two potential energy curves, doesn't matter what these reactions are, but this one here, we see that they're both exothermic in the forward direction. So they're both going downhill. One releases a little bit of energy, one releases a lot more. Let's look at the reverse reactions. This reverse reaction on the left requires a certain amount of activation energy to occur. The one on the right can also happen. We can also go backwards and convert some of these products back into reactants, but it takes a lot more energy to do that. The barrier that needs to be overcome, that activation energy threshold, is much higher. So this activation energy is relatively low. Okay, might still be a decent amount. So that reverse reaction is, at least comparing the two, much more likely. Oops. And the one on the right, that activation energy barrier is significantly higher. So that reverse reaction is certainly less likely to occur there because it needs so much more energy. When we're talking about a chemical equilibrium, we're talking about really just the forward and reverse reactions happening at the same time. Okay, and not only do they happen at the same time, they happen at the exact same rate. So that little analogy with the ants, they're moving materials from left to right at the exact same rate that they're moving materials from right to left. So in the overall scheme of things, there is no change in the size of the pile on the left and the size on the right, because they're losing some and gaining some at the exact same time. We can apply this to chemicals as well. Okay, if we have a certain amount of our reactant material, this gas, for example, we might reach an equilibrium. Notice I've got a double arrow here. We'll talk about that. That double arrow indicates that we're at equilibrium. So think about this like a little balance. We're in balance from our reactants to our products, and both are there in a certain amount. Okay, they might be the same, might be different. We don't know that quite yet. But what's happening is these reactants are being converted into products. That forward reaction is happening. At the exact same moment in time, some products are being converted back into reactants, which just happens to be what we call the reverse reaction, backwards. And those are happening at the same time, at the same rate, the same speed. So if we think about reaching equilibrium here, so to reach chemical equilibrium, let's imagine that we start a reaction with some reactants. That's typically how we start a reaction. We've got our starting materials. We don't have any product yet because we haven't started our reaction. As that forward reaction begins and collisions between A and B start happening, well, we start to form a little bit of product. Let's call that AB. Now, as we're forming a little bit of product, notice my forward reaction, the rate I'm going to indicate by the size of the arrow. It's still fairly quick, but now that I've got some of this product available, then we introduce the possibility for the reverse reaction to occur. So that reverse reaction arrow starts to increase. It goes from not happening at all, because we didn't have any product here, we had no product, to now happening a little bit. So it starts to speed up in the reverse reaction. The size of these letters are kind of indicating the relative amounts. So notice we get less reactants. So the amount of my reactant goes down, and it keeps going down over time. The amount of my products went from none to a little bit more. Okay, and when we reach equilibrium, our rates are exactly the same. Okay, so let's look at if I were to graph my rates. Okay, so we're going to look in, let's use red for our forward reaction rate. So notice this is not an amount, it's the actual speed, the rate of the reaction. Okay, so in the forward reaction, we start off with the highest rate we're ever going to have. We saw this back in Unit 1. Who cares what the number is? We don't need to look at a specific example here. But generally speaking, our forward rate is going to be the highest at the beginning. And my reverse rate, well, I don't have any products yet, so my reverse rate starts at 0, because I can't go in the reverse reaction if I don't have any materials to begin with on the product side. So I start at 0 there. Okay, what's going to happen? Let's focus up here on the forward reaction rate. What's going to happen to that forward reaction rate over time? Well, we saw back in Unit 1 that it's going to start to decrease. So as we start to use up reactants, our forward rate starts to decrease, and it decreases fairly quickly because there's so many collisions happening at the beginning compared to later on that they start to be used up pretty quickly. What's going to happen to my reverse rate? My reverse reaction rate, let's just get a blue pen here. My reverse reaction rate starts at 0. I don't have any product. And then I start making product really quickly. So as soon as I start making product quickly, that reverse reaction rate starts to increase pretty quickly at the beginning. Next up, I just realized number 3 is on there already. So next up, if we focus back on our forward reaction, well, as we start to use up reactants, what happens to the possibility of these reactants colliding with each other? Well, if I have less reactants, then the possibility of them colliding and reacting becomes less as well. So it decreases. So my rate starts to decrease, still decreases, but not as quickly. So it starts to slow down. Well, it's not a very good curve. So it starts to slow down here. Let's get rid of that. Try again. So it decreased quickly at the beginning, and then it decreased at a slower rate later on. Okay, we're going to notice our reverse rate do something very similar. And as we start to form more products, that reverse reaction gets more likely. So my reverse rate starts to speed up. Okay, but it starts to taper off as well. Back to my forward rate, it continues to slow down. But this is my forward rate just sort of slowing down, and kind of petering off a little bit. And it's still going though. Notice it's still happening. It's not going down to 0. And my reverse rate still increases. And they reach this point in time where they happen to be at the exact same rate. So my reverse rate and my forward rate, I'll try and do that, are happening at the exact same rate. It doesn't necessarily have to meet right in the middle. It could be happening much faster or much slower. It totally depends on the equilibrium. So they don't happen to meet right kind of halfway between the two. Okay, so big vocab here on this rate curve. We see our forward rate decreasing. We saw that in Unit 1. Well, now my reverse rate starts to increase, and they meet somewhere in between there. As soon as they've reached the same rate, at that moment in time, whenever that is, then we've reached, I think I've got it written on here, then we've reached, there we go, both reactions happen at the same rate, and we've reached what we call equilibrium, is what we're going to call that. So equilibrium is the point in time, okay, or we've reached equilibrium at that time when the rates have become equal. So that forward rate is happening, and that reverse rate is happening the exact same time, just like those ants walking back and forth, but they are happening at the exact same rate. Okay, reactants are turning into products, which I could write like this, and then products are turning into reactants at the exact same time, at the exact same rate. So here are the characteristics, the things that'll be happening that are true for a system at equilibrium. First one is, and we've said this, the rates in the forward and reverse directions are equal. Notice it doesn't mean your reaction stops, okay? It's really kind of tempting to say that everything stops, because if we were to watch this in person, and we'll do this in the lab, a system at equilibrium is happening in the forward direction and the reverse direction, it's going to look like the reaction stops and nothing's happening, but it only looks like nothing's happening because you can think of these as canceling each other out, okay? Notice the concentrations are not necessarily the same. The rates forward and reverse are the same, but it doesn't mean I have the same amounts of reactants and products. I could have totally different amounts. It just totally depends on that equilibrium system, okay? But they do become constant. They become not changing, okay? And we saw that with the pile with the ants. We had a larger pile on the left, smaller pile on the right, okay? And if those ants move some from left to right and an equal amount from right to left at the same time, they cancel each other out, and so those piles aren't going to change. Point number 2, microscopic processes are happening, right? Things are happening. If we were able to look down at the chemical level, the atomic level, then we'd theoretically be able to see, reactants turning into products and products turning back into reactants, but we can't see that, obviously. All we can see are, the size of these piles in a lab, so it's going to look like nothing's happening. So macroscopic, the kind of big picture, things that you can observe with your senses, they're going to observe as though they're going to appear as though they do not change. They're going to be constant. But microscopically, things are definitely happening. Point number 3, the system is closed. That just means nothing can get in or out. That's all. And that's super important. If we have a reaction where we're trying to achieve a system at equilibrium, and let's say a product is, like we saw one the other day, a product with hydrogen gas. Well, if we let that gas escape into the room, it's now gone. It's not available anymore. So how can that hydrogen gas turn back into a product if it's escaped? So we would have to seal that system. In that case, we'd have to contain that in a container so that we don't let anything escape. That's all. We also need to have constant temperature, and we'll talk later on about temperature's effect on equilibrium. And the last point here, equilibrium can be approached from the left or the right. That just means you can start with a bunch of reactants and eventually reach an equilibrium with your products. You could also start with the material on the right, which we're calling our products, and they would start to turn into materials on the left, our reactants, but eventually we could reach that same balance, that same equilibrium. So here's another analogy. So here we've got our reactants on the left, A and B. We've got our products on the right, C and D. They are in balance, okay? So the forward rate and the reverse rate are both happening, that double arrow, at the exact same time, at the exact same rate. Good analogy down here, similar to that ants one. We've got 2 piles, pile in the hole, pile outside the hole. Notice the sizes are completely different, and that would be analogous to our concentrations. I'll use square brackets here. The concentration of my reactants and products does not have to be the same, But what's happening if person number 1 is shoveling out dirt and person number 2 is shoveling in dirt at the exact same time? So a scoopful of dirt goes out, a scoopful of dirt goes in at the exact same time. If it happened instantaneously and we couldn't see them actually shoveling, then what would we see? We would see these piles stay exactly the same size. And it's because the rate of removal cancels out the rate of putting it in, whatever you want to call that, okay? So following things at equilibrium, really important to understand this. The forward and reverse rates are equal, the concentrations are not equal. So just to visualize this, these are concentration curves here, not rate curves. So we know that the reactants, the concentration of my reactants should go down over time. We saw that in Unit 1. And the amount of my products should increase over time. Okay, so notice when these become constant, so they're constant concentrations, we've reached equilibrium. Okay, they don't have to be the same concentration. The piles of dirt on the last slide don't have to be the same size piles. They're just going to stay the same size as they shovel them in and shovel it out. Okay, so where they end up, the amount of reactants and products, we don't know yet. These are just random examples, but it just totally depends on the reaction you're talking about. So concentrations become constant, they stop changing, and that's our flat line here. Okay, the concentration is not going up or down, but they do not necessarily become equal. They might, it's just, so they might become equal like this. It's just not random, but it depends on the system, okay? So a little vocab here. The left-hand side, this curve on the left, we would say, and this is super important vocab, we would say that this reaction favors the reactant side. And the reason for that is once we reach equilibrium, notice we've got an amount of our reactants. The amount of my reactants is higher. I've got more reactants than I do products at equilibrium. So we say that it favors the left-hand side, the reactant side. The one on the right-hand side, once we reach equilibrium, which is right about here in time, we have more products. Our product concentration is higher than our reactant concentration. So we say that it favors the product side, okay? So it kind of, the analogy there would be which pile is larger, okay? And that shoveling analogy. Is the pile in the hole at the beginning or the pile out the hole at the end larger? And which side is favored, we say. Okay, I'm going to stop there. It's a fairly quick introduction to equilibrium, and we'll look at more of that in the next lesson.